Yesterday, one of her babies.
Yes, I have. Try. I try to give it to. Honey, did I give you?
It's
Yours?
fine.
Okay.
Oh.
Sorry, sorry.
Thank you.
All right, everybody. How did nomenclature practice go yesterday? I know it's not fun, but hopefully it'll at least cement everything in your head so that you'll be able to get everything right. So today we're going to keep doing more practice with Lewis dot structures and talking about more shapes of molecules. And the shapes of these molecules, just because I've already started saying it, it's called valence, shell, electron, pair, repulsion, which we abbreviate as VSEPR, even though the acronym would be VSEPR, but VSEPR doesn't roll off the tongue as well, so we call it VSEPR, even though it's not pronounced properly. So when you say VSEPR geometries, that's what we're talking about. It's just how do we arrange these things in 3 dimensions so that all of these electron domains are as far apart from each other as possible. And so that's what we're going to be spending our time on today. But let's start with Lewis dot structures. So reminder where we started. So what are our criteria for if we did a good job on the Lewis dot structure? How do we know we got it right? Full valences, but what's the first criteria? Even more than getting the right, filling all the valences, right number of electrons. So I'm going to write our checklist over here. It's got to be the right number of electrons because we can't make up matter out of nothing, right? And then we look for, is there a way we can arrange, we can fill all the valences? And then the other aspect that we will introduce today, when we start talking about these, is called formal charge. And that's formal charge is one of the ways that we can use to determine if we put everything in the right spot, if we pick the right central atom, if we arrange the electrons in the best way possible. Because it turns out sometimes there's more than one way to fill these first 2 criteria, but there's one way that's better than the other. And formal charge is going to be the way we evaluate that. All right, so let's start with SO2. And where should we start with SO2? What's the first step with these? Put S in the middle. Why? How do we know it has the most bonds? It's not oxygen. Because there's only one of them. That's a good hint, but that's not always the right answer. I'm going to introduce another idea that we've kind of been dancing around for a little bit, and it's this idea of what's called electronegativity. Electronegativity, is basically how well atoms share electrons. Something that's really electronegative does not share very well. You can think of the elements that are most electronegative as being kind of bullies. They technically share and make these covalent bonds, but they don't share evenly. Right? And the way we know that sulfur goes in the middle and not oxygen is because oxygen is more electronegative than sulfur is. And it's one of those periodic trends, just like atomic radius, And just like ionization energy, when we're talking about electronegativity, it's tied to ionization energy, because ionization energy was defined as what? Anybody remember? How much energy does it take to remove an electron? So something that has a really high ionization energy, it's really hard to take an electron away, which also stands to reason it doesn't share very well either. Right? If something has really high electron or ionization energy, for the most part, that also means it's very electronegative. If you make a covalent bond with that element, it's not going to be shared evenly. So who remembers where the highest ionization energies were? So top right, and especially the noble gases, and that's where electronegativity and ionization energy are a little bit different, because our noble gases, for the most part, don't make covalent bonds. So if they don't make covalent bonds, they can't really be electronegative. They're so bad at sharing that they don't share at all. Not only do they not share evenly, they just don't share, period. And so the noble gases are the only children. They don't have to share at all. The most electronegative elements are the ones that'll share, but they don't like it. They're not good at it. And it is that top right corner. Fluorine is the most electronegative. And then it kind of is, the closer you are to fluorine, the more electronegative it is, but it's mostly that top row. Nitrogen, oxygen, fluorine, and then chlorine are most electronegative elements. Fluorine being the most electronegative, but then oxygen is the second most. So how does this help us? Well, if these are the elements that don't share very well, do they want to be in the middle? No, because we started by saying we're going to put the element in the middle that's going to make the most bonds, right? If they're really bad at sharing, we're not going to put them in the middle and make them share more. And so when we're looking at this list, we're trying to decide whatever's the least electronegative is going to go in the middle. Right? And that's also, that electronegativity is also why that stair-step line between the metals and the metals is oriented the way it is. If you look at it, it's basically a line that's like delineating a certain distance from fluorine. Right, so fluorine's your most electronegative, and every step away from fluorine, you get a little bit less electronegative until you get to the point where you get metals. And once you get to metals, we're not making covalent bonds anymore. Turns out, if you're careful, you can make covalent bonds with metals, but they're pretty uncommon. And again, take OChem and we'll talk more about that. All right, so that's how we know the sulfur is going to be in the middle. Now we're going to put our oxygens on either side. And what else do we need to know in order to get a Lewis dot structure? Right number of electrons, right? Specifically valence electrons. So how many valence electrons do we get for sulfur dioxide? We get 6 from the sulfur and then 6 from each oxygen too, right? So 6 electrons plus 2 times 6 electrons, 18 electrons total. Because they're in the same column, so they're both, even though the sulfur is less electronegative than the oxygen, they have the same number of valence electrons. All right, so now what do we do? Next step. Yeah, we're going to start by filling up the outside, but I guess before we do that, even we might as well do those bonds, right? So that just added, we just used up 4 electrons, so we have 14 electrons left. And now we can start on the outside and work our way in. How many is it going to take to fill up the oxygens from here? Each oxygen still needs another, how many? Another 6. So 2, 4, 6, 8, 10, 12. Two electrons left. Where are they going to go? They can't go on the oxygen because the oxygen's already got a full valence, right? So they've got to go on the sulfur. We done? Do we meet our first criteria? We use the right number of electrons? Yep. Did we fill all the valences yet? No, sulfur still needs another pair. But we ran out of electrons, so what do? Make a double bond. So it doesn't really matter which oxygen you pick. Pick an oxygen, erase a lone pair, and turn it into a double bond. Now did we fill all the valences? Criteria 1's still good. Criteria 2, we're good. This is a valid Lewis dot structure. It still might not be the best Lewis dot structure, though. And so there's two concepts we're going to introduce now. Formal charge. Formal charge is basically, it's a way of seeing how well the electrons are shared compared to how many electrons the element has on the periodic table. These electrons that are in these bonds are being shared. Each bond is a pair of electrons, right? But they're not actually, the sulfur doesn't actually own both of these electrons. It owns one of those electrons, right? We made this bond by bringing one electron from the sulfur up to one electron from the oxygen. Then when their orbitals overlap, we've made a covalent bond, right? Formal charge is basically looking at bonds and lone pairs and comparing the number of electrons this sulfur has to how many electrons it has on the periodic table. So on the periodic table, how many valence electrons does sulfur have? How many valence electrons does sulfur have now if you count the shared ones? It's got 8, so it's got a full valence. But how many does it own out of those 8? It owns those outright, right? It's not sharing these at all. But all of these bonds, it really only owns half of those electrons, right? Because they're being shared. If you bought an e-bike with your sibling, do you own a whole e-bike? No, some of the time you own a whole e-bike, but really you own about half of an e-bike, right? So these bonds, even though they have 2 electrons in them, the sulfur only owns one of the electrons there. So how many electrons does the sulfur, quote unquote, own? 3 from the bonds plus the 2 that it owns outright. Right, so that means that it really only owns 5 electrons. And how many electrons does it have on the periodic table? So it's missing 1 electron, right? Which would give it what charge? It's missing an electron, which gives it a positive charge. Right, so our formal charge is number of electrons. Make sure I get the sign properly. Number of electrons on periodic table minus number of electrons owned. So it owns 5 on the periodic, it owns 6 on the periodic table. It owns 5 in this Lewis dot structure. And I keep saying owns like electrons have some concept of property or consciousness. We know that's not really true, right? That's just a convenient way of describing this. All right. So if we use that same idea, what's the formal charge for this oxygen here? How many electrons does it own? 6. It has 4 that it owns outright, and then 4 that are shared. The count is 1 apiece. right? So that means it owns 6 and it has 6 on the periodic table as well, right? So this oxygen has a formal charge of 0. That's really good. Formal charge of 0 means it's pretty stable. So that's our last criteria here is if we drew our Lewis dot structure properly, it keeps all of our formal charges as close to 0 as possible. 0 charge is stable. And so this oxygen is stable. The sulfur +1 is kind of close to 0. It could be better if we rearrange things maybe. What's the formal charge on the other oxygen? Yeah, it owns 6 outright plus a bond. So it owns 7 electrons. So that's 1 extra electron. So its formal charge is -1. So if you do this right, this can also help you figure out if you use the right number of electrons, because your formal charges should always add up to the overall charge of the molecule, or you did something wrong somewhere. So in this case, 0 + 1 and a -1, everything adds up to 0, and our molecule has a charge of 0. So that's an indicator that we did our formal charges properly. We counted our electrons properly. Could we make these charges closer to 0 though? How? We double bonded it twice. This oxygen has minus charge, right? Which means it's got too many electrons. Sulfur's got a +1, which means it's got too few electrons. We take another lone pair and turn it into a double bond. Now the sulfur owns 6 electrons, right? 4 in the form of bonds and then a lone pair that it owns outright. The oxygen owns 6 electrons now. So now both of these formal charges are 0. The way we drew it first was an okay Lewis dot structure. This is a better Lewis dot structure. Except we kind of broke a rule to do that, didn't we? Anything about this raising a red flag? What? It's got 10 valence electrons. We're used to dealing with only 8 valence electrons, or just 2 electrons if it's hydrogen, right? So what is it about sulfur? Is this even possible? Well, I drew it and told you that it looked better, right? It turns out you can go above 8 valence electrons if your element is in the 3rd row of the periodic table or lower. What changes when you get to the 3rd row of the periodic table? We bring the D block into it. Right, so sulfur doesn't have any electrons in a D block, but it has a D block present in its valence shell, right? Because sulfur's valence energy level is n = 3, right? And the first D orbital shows up in n = 3. So basically, when you get to the 3rd row of the periodic table, you need at least 8 electrons to fill the valence, or for it to be considered having a full valence, but you can go above that if it lowers or gets your formal charges closer to 0. That it causes it to become more stable, right? So if it was going to make it less stable, we wouldn't actually see it, but we can actually measure bond lengths and the way that this compound behaves in its geometry, and we can actually see that it's behaving like it has 2 double bonds. And that these electrons are all in the 3rd energy level. So it actually matches with what we can't see, even though it seems like we're breaking one of our rules. We will only ever do that from the 3rd row and down. Oxygen can never have more than 8 electrons. Nitrogen can never have more than 8 electrons. Most importantly, since I'm an organic chemist, carbon will never have more than 8 electrons. It's a pet peeve of organic professors everywhere. when you see a carbon with 5 bonds. Can't happen. No faster way to put your chem teacher in a bad mood than to draw a carbon with 5 bonds. And so, but once you get to the third row, all that changes. The third row, you can have more than 8 electrons, specifically if it's going to get your formal charge closer to 0. All right. Now I think you know everything you need to know about Lewis dot structures, so we can just keep practicing them now, and we'll get really good at it. Let's try one of these other ones. Let's do HCN. We're naming HCN. What type of compound is that? Acid, because it looks like it's an ionic compound, but with hydrogen as the cation, right? What would we name it then? What is the anion? Cyanide. And if it ends in "ide," what do you do for the name? That's ite. It's the hydroic. Remember, the simplest compounds have the most complicated name. Ide turns into hydroic. So HCN would be hydrocyanic acid. Fun fact, does anybody know why cyanide, where the name for cyanide came from? Look at the root. What does cyanide come from? An element? It comes from the color. It does. Actually, the earliest really blue cyan paints were made with cyanide. They knew it was really, really poisonous, but it also gave you really, really good colors. So if you've ever watched Bob Ross, if you haven't, I highly recommend that you do. It's a very calming way to end the day. But anytime Bob Ross talks about Prussian blue, it's actually a paint that's really high in cyanide. That's what gives it the blue color. All right, so if we're going to look at HCN and do a Lewis dot structure for it, what are we going to put in the middle? Hydrogen is the least electronegative, but can hydrogen ever go in the middle? How many bonds does hydrogen need to make? Just 1. So if it can only make 1 bond, even though it's the least electronegative, we can't put it in the middle just because you can't put something in the middle that's only going to make 1 bond. So with that in mind, we know it's not hydrogen in the middle, so what goes in the middle? Carbon or nitrogen? Carbon. All right, then we start by counting up our electrons. How many electrons do we have to work with? 1 and 4. 1 electron from the hydrogen, 4 electrons from the carbon, 5 electrons from the nitrogen. 10 electrons total. Start by using 4 of them up there. 6 electrons left. Now what do we do? We do the dots where though? Technically, you could do it on either, you could start in either spot, but I like to start at the outside and work my way in. So I'd start with the nitrogen. Nitrogen's stable, but we're out of electrons. So what do we have to do next? Make a double bond. Erase a lone pair, turn it into another bond there. We good? Still use the right number of electrons. Does everything have a full valence though? No, not yet. So we do it again. That fills our first criteria, right? fills our second criteria. Does that get our formal charge closest to zero? What's our formal charge on the hydrogen? It owns 1 electron. How many does it have on the periodic table? Also 1. So we're set there, right? The formal charge is 0. Carbon owns 4, all in the form of bonds, right? And it has 4 on the periodic table. So formal charge is 0. Nitrogen owns 5, 2 that it owns outright and 3 from bonds. And it has 5 on the periodic table. So we're good. This is also how the formal charge is also how you know that you picked the right atom to put in the middle. If we didn't think about electronegativity, what do we get if we swap the carbon and the nitrogen? We still use the same number of electrons and we still filled all the valences, right? But now the formal charge on the nitrogen is what? +1. It owns 4 and it started with 5. So it lost an electron. The carbon owns 5 and it started with 4. Ready? So sometimes you have to have a charge on something. So these are in order of importance, right? We can't add more electrons than we have, and we need to fill valences. Sometimes we can overfill valences, and sometimes there's a better way to arrange them by switching what's the middle atom. But you have to go in order of importance. If there's only one way to arrange things so that you use the right number of electrons and you filled all the valences, sometimes you'll still wind up with charges on things. That's what we're going to look at next with nitrate. All right, so, but before we do that, I just want to finish the point that we could have written it like this. This is still a valid Lewis dot structure for the first 2 criteria. It's just not the best Lewis dot structure. Because the best Lewis dot structure would be if we switch these. Carbon goes in the middle, nitrogen on the outside. And then everything has a formal charge of 0. What kind of shape will this make? What's the furthest apart? How many electron domains are there around that carbon? How many things are taking up space around the carbon? 2. You've got the hydrogen bond taking up space. And even though there's a triple bond here, they're all in between the same 2 atoms. They're still only taking up, that's only one object taking up space or domain. So what's the furthest apart you can get 2 things? How do we rank it? Distance in these. It's not really a distance, it's a what? The angles, right? So with only 2 things around this carbon, the furthest apart they can be is 180 degrees. So we would say that the geometry of this molecule is linear, or especially this carbon. Turns out as we get larger and larger molecules, we can every atom has its own geometry. So we talk about this carbon has a linear geometry. Let me go back to our sulfur dioxide. How many things are taking up space around the sulfur? Do the lone pairs count? Are they still going to push away other electrons? Yeah. So lone pairs still count. So we have 3 things taking up space. So in terms of angles, you have three things. What's the furthest apart that could be? We get further than 109. You have 360 degrees to work with around sulfur. You divvy that up into three chunks, 120 degrees. So we would get something that looks like this, where you have roughly 120 degrees between your electron domains. Did we need to use 3 dimensions to do that? No, so this is still a flat molecule. And the way we say flat mathematically, anybody know term for flat mathematically? 2D. Things that are 2D are said to exist within the same plane, right? So we call it planar. And to say that we have 3 things all in the same plane, 3 things splitting this up, we call it trigonal planar. So we've got linear, we've got trigonal planar, and then we had that, as soon as we get more than 3 objects around our central atom, we have to start using 3 dimensions, and that's when things get tricky. Right, so we'll spend more time with that in a few minutes. I'm just trying to introduce these geometric terms slowly, rather than overwhelming you all at once. Especially since these ones are actually linear and trigonal planar are pretty easy to visualize. All right, let's look at nitrate. What's going to go in the middle? N. Oxygen's our second most electronegative element. Oxygen will never be in the middle, with 2 exceptions. The only time oxygen will ever be in the middle is if hydrogen is involved, because hydrogen can't be in the middle, or if fluorine is involved, because fluorine is the only element that's a bigger bully than oxygen. So we're going to put nitrogen in the middle, surrounded by oxygens. How many electrons do we have to work with? So 5 from the nitrogen, 3 oxygens, and each oxygen brings 6 electrons. Who said 24? I heard somebody say it. We've got a negative charge, right? Negative charge means what? We get 1 extra electron. 1 electron just for the charge. So anytime we have a polyatomic ion that we want to do a Lewis dot structure for, all of our same rules apply. We just use that charge to modify our total number of electrons at the end. So if we got a -1 charge, that means we get 1 extra electron. That gives us a total of 24. 18 and 5, 23 plus 1 extra 1, 24 electrons. Somebody said the right answer and they didn't want to claim credit for it. I heard somebody, maybe it was just wishful thinking. Maybe I imagined it. All right, now how do we arrange these? We'll start with that, right? That used 6 electrons, so now we're down to 18 electrons. Each oxygen still needs another 6, right? Starting to look familiar. Each oxygen needs 6, and there's 3 oxygens. That's going to be our 18 electrons right there, right? No electrons left. So we use the right number of electrons. Criteria 1. Our most important criteria is good. Can we shuffle things around to fill criteria too? How do we do that? Pick a lone pair and make it into a double bond. Does it matter which oxygen I picked? Pick one. You got to pick one, but it doesn't make a difference. In reality, what will actually wind up happening is they kind of share responsibility for the double bond. They wind up all taking a turn, kind of. So like a third of the time, this oxygen has a double bond, and a third of the time, this oxygen has a double bond. Third of the time, this oxygen has a double bond. Although it doesn't really behave like that because it's quantum mechanics. So it's kind of like they all share a third of a bond all at the same time. It's weird because its orbitals are involved. If you ever heard somebody use the word resonance to talk about electrons, that's what they're talking about. It's the fact that you really have this, or this has a double bond, or this has a double bond all simultaneously. It's a Schrodinger's cat situation. All right, so now we use the right number of electrons. We still used our 24 electrons, as long as we remembered to erase that lone pair. We filled all the valences. What are our formal charges? We know that they're not all going to be zero, because our formal charges are going to have to add up to -1. What's the formal charge on this bottom oxygen? It owns 6 and it has 6 on the periodic table. So formal charge is 0. Right? 2 that it owns outright, 4 electrons in bonds, and it owns half of those. So total of 6. These other 2, they have the same number of lone pairs and bonds, right? So we can they're going to be the same formal charge. They're both going to be what? -1. They each have 1 extra electron, and because electrons are negative, they're both -1. Then what about the nitrogen in the middle? Nitrogen's owns 4 electrons and has 5 on the periodic table. So it's got a +1. Does that add up to -1 overall? So we counted our electrons properly and we did our formal charge properly. Is there a way we could rearrange this to get some of these to be closer to 0? Without breaking the octet rule. Because remember, we're not allowed to break the octet rule for nitrogen because it's in the second row. It doesn't have a d orbital to use. So if this was a sulfur, we'd be allowed to make more double bonds to get things closer to 0. But because it's nitrogen, we can't. So this is the best we can do. Everything's got a full valence. We've got the right number of electrons. And we got our formal charges close-ish to 0. Yeah. Because you're memorizing your polyatomic ions, including the charges. Oh. Well, we can measure that there's, you mean like how did they originally figure this out? Basically, they could measure, so say they measured sodium nitrates % by mass. And they could figure out, okay, well, this is a molecule where we've got one sodium ion, and then we have 1 nitrogen and 3 oxygens all together, adding up to a -1 charge because this group of atoms was in a 1-to-1 ratio with sodium. So part of it was just we knew what the metal ions were first. And then once we compare the metal ions to these polyatomic ions, we can work backwards to figure out the charge on the polyatomics. That answer your question? On a theoretical side, it's because you need an even number of electrons to fill all the valences and not have unpaired electrons. So, and they really did kind of figure those out simultaneously. The theory and experiment oftentimes are they're neck and neck. They're kind of proving the same things from opposite ends sometimes if they're doing it right. Because what will happen is theory will come forward with some wild idea like Schrodinger's cat. And then the experimentalists are like, well, that can't be true. Well, I'm going to disprove that. And then what they wind up showing is, well, actually, there is a lot of evidence to say that some of these weird quantum mechanics ideas actually are true at quantum scales. So experiment and theory kind of fight with each other a little bit, but at the same time, they should work together to reach the same ideas at the end. And that's kind of what we see with things like nitrate's charge. We have to have an even number of electrons, and if nitrogen is involved, that means there's got to be a negative charge somewhere, or a charge of some sort anyway. All right, how are we feeling about these? Ready to think about geometry a little bit more? Here's another slide on formal charge, just to make the same point that we already did on the board a minute ago. So here's a molecule that has two possible Lewis dot structures. How do we know which of these is right? Okay. Count the charges. Which one keeps the formal charges closest to zero? The first one. The first one gives the carbon a formal charge 0, and the sulfur gets a formal charge 0. Over here, sulfur's got 4 electrons, and it's got 6 on the periodic table. So that would give the sulfur a +2 charge, and the carbon a -2 charge. That's less stable. Even if we were able to take out our atomic tweezers and move things around to make this molecule, it's going to spontaneously rearrange to do that, because this is lower in energy, more stable. So, that is actually what we see. If we temporarily make an unstable state where things don't have the right formal charge or formal charge close to 0, really quickly the electrons will move themselves to correct that, to get to that lowest possible energy state. All right. We've done enough practice there. So here's the background on that VSEPR geometry. And if you actually run the numbers on the volume of the atom compared to the volume of the nucleus, you'll find out that 99.994% or so of an atom's volume is made of electrons. Electrons are all negatively charged, and similar charges repel. So what does that give us? It gives us VSEPR geometry. The idea that these electron domains are going to push each other away as far as possible. And that means that we have to start thinking in terms of angles and shapes, not just thinking in formal charge. We're moving past that now. Has anybody heard of Richard Feynman before? He's a theoretical physicist. He was one of the young physicists that was working on the Manhattan Project. He was in Oppenheimer, but just as a bit role. I think he had like 2 speaking lines. But Feynman was the one who figured out a way to qualitatively show interactions between fundamental particles. So this is called a Feynman diagram. Really kind of interesting. It's one of the few times he basically won a Nobel Prize for drawing pictures. Because he said, well, you can show what this force looks like, input numbers to it and do all the math to it. But you can also show it qualitatively by just showing these 2 electrons, when they get close to each other, push on each other and move the other direction. So if we have 2 electron domains, they're going to arrange themselves to be 180 degrees apart. And we called that what? Linear. If we have 3 clouds of electron density, they're going to arrange so that they're 120 degrees from each other. We called that trigonal planar. And then once we get past 3 clouds of electron domains, we have to start thinking in 3 dimensions. Right? Because if we just kept it flat, if we looked at CH4, we actually usually name with the organic nomenclature, that's methane, which is a major component of natural gas. Methane doesn't have just 90 degrees between these bonds. It has 109 degrees. Right? And the way that we show that on a flat surface is by using these dotted lines to represent something goes into the board, and a wedge to indicate something comes out of the board towards you. If you squint and tilt your head just right, you can kind of see that looks kind of like I'm trying to take a flat bond and pointing the end of it towards you. If you really wanted to, you could make it like a cylinder, I guess, if you're really good at using force perspective. But the standard way is to just use a triangle like that we call a wedge. What that actually looks like in 3 dimensions, if we actually can represent it in 3 dimensions, is you get something like this. Right? So remember how we said that it doesn't really matter that all of these hydrogens are identical to each other. All these positions, we got to that because we were talking about water. We said it didn't matter if you drew water like this or like this, because all of these 4 different electron clouds were all identical to each other. It's kind of hard to see when we draw it like this, but if we actually have a 3-dimensional model to look at, you can see if you look at hydrogen 2, it's adjacent to 3, 4, and 5. Right? So what that actually means is that hydrogen 2 is equally close to all 3 of the other electron clouds. In other words, it doesn't really matter whether we drew our hydrogen like this or like this, or our water, I mean, because in either case, this hydrogen is equally close to these to all 3 of the other electron clouds, which is hard to visualize a little bit. I get that. Which is why next week's lab will actually have you bring in your laptop or Chromebook, and you'll actually play around in 3 dimensions on your computer, building these structures, dragging them around, taking your time and trying to visualize them. And I think we have some molecular modeling kits as well. So if you prefer to build them in 3D and then compare them, we actually have a bunch of atomic models for building these out. Basically, instead of building this on the computer screen and clicking and dragging around, you can actually build it out of balls and sticks. Thank you. If you get really into this sort of thing, these are actually really cheap online as well. They're $20 for one of these kits. And if you're going to continue taking science classes, it's not a bad idea to have these. Partly just because it's kind of fun to build them. It's like building Legos. All right, so when you have something like this, actually holding it in your hands is even better than that, unless you're really used to looking at computer screens and playing video games, that kind of thing. But you can see the bond that I am holding in my hand is equally close to all 3 of the others, which means it's identical to all 3 of the others. Every single hydrogen, every single one of these bonds has 3 nearest neighbors that are all 109 degrees apart from each other. right? And what do we call that shape? It makes a four-sided object when you look at it, right? Four-sided shape is a tetrahedron. Leonor?
Reality, like central atom actually larger, is you just do that to the scale.
It is, so remember that atomic radius is based mostly on how many electron energy levels are occupied. So everything on the second row of the periodic table is going to be pretty close to the same size. But if we're comparing carbons to hydrogens, hydrogens are going to be much smaller. Even when they're in a covalent bond, they're still not going to be the same size as the others. And really, there's some fluctuation. And we don't just make generalizations and have plastic models. What my part of my research in grad school was actually calculating these geometries of these three-dimensional molecules, because, like you said, that a carbon to oxygen bond is a little bit different in size than a carbon to a nitrogen bond or a carbon to carbon bond, because all these different atoms all have slightly different atomic radii and different orbital energies. So we do make some simplifications. They're not actually all going to be the exact same size. And if you want to play around with looking at what some of these other molecules look like, there's a good tool online called MoleView. MoleView is my favorite free online, easy to use chemical drawing software, because one, you can build your molecule by connecting all these different atoms together, and then it's got a button that says 2D to 3D, and it'll actually show you what it looks like in 3 dimensions. And then you can click and drag around here to actually look at what these different molecules look like. And so obviously this is getting a lot bigger than just looking at one central atom. Technically, every single one of these atoms that's being shown here, I guess other than the hydrogens, could be considered a central atom, the way we're thinking about it over here. And when you put all of these geometries together, you get an overall shape for the total molecule. But each of these individually, we can look at that and say, okay, well, that carbon has 3 electron domains around it, so it's going to be trigonal planar. And it's going to be roughly 120 degrees between them. You put this trigonal planar atom with that trigonal planar atom, and put all of that together, and you get an overall shape of the molecule. Yeah? No, I do at this level. This is just, in OChem, we frequently don't, because everything that's not explicitly stated is assumed to be a carbon, because organic chemistry only cares about carbons. And there's actually, you can actually force it to show that. So this would be the way that I would want you to draw that, but we're not going to get to anything this complicated. Anybody know what that molecule is? Sometimes it's one of those ones chemists always see as stickers or tattoos, or we could actually count all the carbons. It's caffeine. So very chemist joke. Have a coffee mug with caffeine molecule drawn on the outside. The other one that we see all the time, it's usually not done very well, is a neurotransmitter called serotonin. Serotonin looks like that. And yeah, we frequently see, that's a really common one. We see that on tattoos all the time. Somebody has a tattoo of a molecule you don't recognize, 9 times out of 10, it's serotonin. And the 10th time, it's some random drug that looks really close to serotonin. Why do they do serotonin? So serotonin is one of the things that's responsible for, one of the neurotransmitters that's responsible for regulating emotion. And it's been tied, they're not sure of the exact mechanism, how it works, but low serotonin levels are tied to clinical depression. And high serotonin levels are tied to, really high levels are tied to schizophrenia and hallucinations. So it's a fine line, but most antidepressants work by increasing your serotonin levels. And a lot of antipsychotic drugs work by reducing your serotonin levels. So it winds up being a really important molecule in neurology and in clinical psychology. Most antidepressants these days are SSRIs, which stands for selective serotonin reuptake inhibitor. Back to you.
And often have depression.
A lot of times people that are schizophrenic go off their meds because their meds give them a feeling of depression. So it's not necessary. It's almost like a bipolar situation where when you're in a schizophrenic episode, your serotonin levels are way too high. And when you're in a depressive episode, your serotonin levels are too low. But it's not quite as simple as that. We still don't know exactly how all these different psychological disorders and moods and emotion all work together, but we do know serotonin is an important one. It's also the one that's really close to most hallucinogens work by basically they either trigger a flood of serotonin, which can cause hallucinations, or they impersonate serotonin and basically get in the way of the way your body naturally breaks down serotonin. And that causes temporary hallucinations. But that's also why if you have a family history of mental illness, especially bipolar or schizophrenia, don't mess around with hallucinogens. Because if you're predisposed to that, it can tip you over into full-blown schizophrenia because you wanted to try acid once. So know your family history before you mess around with anything in your brain chemistry, for sure. And don't do drugs. All right. So since we have all these different possibilities, the only three we've talked about so far are linear, trigonal planar, and tetrahedral. But once we start getting to the third row of the periodic table and below, once we can break the octet rule, we actually have a couple of other common geometries. Again, these can only happen once you get to the third row of the periodic table and below, because you have to have more than 4 electron domains in order to get to these bottom two shapes. And so these bottom two shapes, if you have 5 electron groups, the furthest apart you can have them, it looks like a trigonal planar kind of fused with linear. If you take a trigonal planar shape, so everything's 120 degrees from it, and make that flat into the board and out of the board, and then you stick one more atom sticking straight up and one more sticking straight down, you get something that looks like it's trigonal planar pyramid shape. So they call it trigonal bipyramidal. Or the other way you can think about it is it looks kind of like taking 2 tetrahedrons and stacking them on top of each other. And it makes it a little bit tricky to draw, but basically you just draw them kind of T-shaped, and then on the other side you get one coming out of the board and one going into the board. So if I was drawing it by hand and trying to show the geometry, there's ones that are kind of T-shaped, and then one going behind the board, one coming out of the board towards us. You can kind of see how that gives you that overall shape of 2 3-sided pyramids stacked bottom to bottom.
I want to get confused with multiple bonds when you have like a 3 line.
If you're really careful and you're doing a better job there than I do, it's supposed to look like a wedge like this. Then it's a little bit more obvious what's going on. It is hard to draw a double bond going into the board or coming out of the board. We try not to do that. If one of these has to have a double bond, we typically make it one of the ones that's in the plane of the board, because it's a lot easier to draw double bonds that are in the plane of the board rather than sticking out of the board. And then the last one is the one I drew the other day as well. It's basically, it looks a lot like that trigonal bipyramidal, except with 4 things in the middle. So you kind of have like a square geometry into the board and out of the board where everything is 90 degrees from everything else. And that gives you an overall shape that's called octahedral because it gets, even though there's only 6 things, 6 electron domains around the sulfur here, it creates a shape that has 8 sides. So this is the one that looks like an 8-sided die. Or you can think of it as 2 4-sided. Think of a 4-sided pyramid, like Egyptian pyramids in Giza, stacked bottom to bottom. And that's the overall shape that you get here. And so it's a little bit hard to see again. It takes some practice to be able to see this visually. But there's a square right there, right? If you take that square and make a pyramid going up and a pyramid going down. I guess the way that the perspective is drawn, you can kind of see all 3 sides of the pyramid all at the same time. All right, so 8-sided shape, octahedron, with only 6 points, which is kind of weird to think about. It only takes 6 vertices to make an 8-sided shape. But that is how it works. Turns out working in 3 dimensions is a little tricky sometimes. Maddie? I will not make you draw the lines, just stuff that's written in black. And even I won't even be picky enough to force you to remember the names if you can draw it accurately. So rather than memorize octahedral versus trigonal bipyramidal versus tetrahedral, if you just want to remember what the shapes look like, and you can use the wedges and the dashes to show me that, that's an acceptable way on the midterm to tell me the molecular geometry. Because some of the names, it does get a little bit more tricky because what happens is, turns out if one of those electron domains is a lone pair, we actually can't see the lone pairs. We can only measure where the nuclei are, because the nuclei have masses and have a positive charge. If we have something that has a lone pair, we can see the effect of the lone pair. We can see that it takes up space, but we can't measure it. And the analogy that I use for that is it's sort of like if you're getting onto a school bus and you know it's a really full school bus, but it looks like an empty seat from the front of the bus. But when you get up close, there's actually somebody's backpack sitting there. From the front of the bus, it just looks like nobody's sitting there, but you can see the absence of space. In fact, that nobody else has filled in that space is showing you that the backpack is there without being able to directly see it. And that's kind of the way that electrons work. These lone pairs take up space, they force these geometries, but you can't actually see them visually. So we actually have different terms for all the different molecular geometries. Right, so the electron geometry is always just going to be count how many things take up space. It's always one of those 5 basic ones from this slide. Our electron geometry always is one of these. However, if one of those groups is a lone pair, it has a specific name off of this list. So in particular, like something like ammonia, NH3, has a Lewis-Sott structure that looks like or has an electron geometry that looks like this, the tetrahedral electron geometry. But because we can't see this, just because we can't see it doesn't mean that this flattens out and becomes trigonal planar. It means that we have something that doesn't look like it's fully tetrahedral, but it's based around a tetrahedral shape. So the electron geometry is tetrahedral. The molecular geometry is basically, okay, now erase your lone pairs. And so your molecular geometry, in this case, we go and look at this chart or a similar chart and say it's called a trigonal pyramid. This is what I mean by sometimes it might not be worth it memorizing all of these, and as long as you can draw them. Right, especially when you get up to some of these other ones. Like 5 electron groups with lone pairs starts looking really weird. And memorizing all these different names. Is it a sawhorse or is it T-shaped? And the bottom ones can't even really see. You get octahedral, square pyramid, square planar, T-shaped, and then linear. So obviously it gets a little bit wonky once you get a little bigger, and that's why it's totally acceptable to just be able to draw them properly with approximately the right angle. All right, good job today. See you on Friday. If you didn't get your quiz yet, come up and get it. Other than Hannah. Sorry, I forgot about your thing. I'll have it for you on Friday. There wasn't one over the weekend. You're lucky. No worries.
Yeah, my favorite thing today.